This is Learning Assessment Problem 1113. The problem-solving strategy here is that of three-phase balanced AC power circuits. The problem states that we have two balanced three-phase loads connected to a 480-volt line. The details of the two loads are given, and note that from the units we are specifying the apparent power associated with each of the loads. We'll begin by calculating the apparent power per phase for each of the loads. And this will be the total apparent power stated divided by 3, which for load 1 is equal to 1666.7 volt amperes per phase. For load 2 we have a similar calculation, and this SL2 magnitude will equal 10 kVA divided by 3, which is 3,333.33 volt amperes per phase. Now we can use the power factor information for each load to calculate the angle that the current will lag the voltage in each instance. So theta L1 is equal to the inverse cosine of the power factor for load 1, which is equal to minus 36.87 degrees. Similarly, theta L2 is the inverse cosine of 0.9, and that is equal to minus 25.84 degrees. Both of these are negative angles because we are told that the power factor is lagging, and the angles are a measure of the current with respect to the applied voltage. Now we'll sketch an equivalent circuit based upon a Y-Y type of connection. Here the two loads are shown as connected in parallel across one of the phase voltages in an assumed Y-Y type of three-phase system. The magnitude of the phase voltage will be equal to the line voltage, which has been given to us, divided by the square root of 3, or V sub P is equal to 480 volts divided by the square root of 3, which is 277.13 volts. Now we'll look at the relationships amongst the real power, the apparent power, and the power factor in order to calculate the two load currents. So we have that the power per phase is equal to the magnitude of that voltage phasor for that phase times the magnitude of the current for that particular load times the power factor for that load. And that will also be equal to the magnitude of the load apparent power, or complex power, times the power factor for that load. So for the load current IL1 magnitude, we can calculate that as the apparent power SL1 magnitude times the power factor for load 1 divided by the phase voltage magnitude, and again times the power factor for the load 1, so the power factors will cancel. This is equal to 1666.7 volt amperes apparent power divided by 277.13 volts, which is equal to 6.014 amperes. The load current associated with load 2 will equal in a similar fashion SL2 times the power factor of that second load divided by the phase voltage magnitude times the power factor again, and this is equal to 3,333.33 volt amperes divided by 277.13 volts, and that's equal to 12.028 amperes. Now for the phase angles for these two currents, we can write that IL1 phasor is equal to the magnitude 6.014 at an angle of, and we determine that power factor angle to be minus 36.87 degrees amperes. Similarly, IL2 phasor is equal to 12.028 at an angle of minus 25.84 degrees. In rectangular form, we can write these two currents since we're going to want to add them. IL1 is equal to 4.811 minus J 3.608 amperes, and IL2 is equal to 10.825 minus J 5.243 amperes. So now we'll calculate the line current as the sum of those two load currents, and this is equal to 15.636 minus J 8.851 amperes. Now we can calculate the magnitude of that complex expression for the line current as 17.97 amperes RMS.